Hi, this is Barrett Givens. In this video, I want to prove that there are two particular functions that are continuous, kind of like no matter what topological spaces you're looking at. So these are sort of very special functions. All right. So the first theorem is suppose f goes from a topological space x to a topological space y, and f is a constant function. Then f is continuous. So this is true no matter what spaces x and y are, no matter what topologies x and y have, any constant function is always continuous. And okay, so to see this, we just are going to use the definition of continuity. So our proof will be, okay, let's suppose f goes from x to y. And let's suppose f is a constant function. So I'm going to write that by saying f of x is equal to c for some constant c in y. Okay. The definition of continuity, I want to show that f is continuous. So I have to show that given any open set in y, its pre-image is open in x. So let's let u be open in y. And I don't have any assumptions about y, so there's nothing I can particularly say about u other than that it's an open set in whatever the topology on y happens to be. It could be any crazy topology that you can imagine. Okay. But what is F inverse of u? What is F inverse of u? Well, by definition, F inverse of u is the set of all x such that f of x is in u, which is the set of all x such that c is in u. So it's interesting because that condition, this is a set of all x such that c is in u. There's no x on this condition right here. This doesn't say anything about x anymore. C is in U is either true or it's false. So if C happens to be in U, then the set of all x that make that true would be all the possible x's. And if C is not in U, then the set of all x that makes that true would be no x's. And so this set here, it's either all of x if C is in U, or it's the empty set if C is not in U. So F inverse of U is either X or F inverse of U is empty. It's either the whole space or it's nothing. And it doesn't matter what topology X has, we know that in every topology, the whole space X and the empty set, those are the two sets that always have to be open. Either way, F inverse of U is open. So F is continuous. Okay, so that shows that for any two topological spaces, a constant function is always continuous. That seems like a good thing. All right, let's prove a second theorem that's sort of comparable, similar. So we have our first theorem still written up there. Now the second theorem. Let's suppose f goes from a topological space x to itself, and we'll let f of x be the identity function, which means f of x equals x. Then f is continuous. So for any topological space x, any space x with any topology on it, the identity function is always continuous. And let's prove this. Proof. Suppose x is a topological space. And f of x equals x. We want to prove f is continuous. How do you prove a function is continuous? Well, you have to take an arbitrary open set in the codomain. So let's let u subset of x be open. And then we have to show its pre-image is open. So then the pre-image, that's the set of all x such that f of x is in u by definition, which is the set of all x such that x is in u. So all the x's that are in u, that's just another name for u. Okay, the function f doesn't do anything. It just keeps every point where it is. So the pre-image of any set is itself. The forward image of any set is itself. F just keeps everything where it is. There's no movement happening. So if U is open, then the pre-image of U is also U, which is still open. So F inverse of U is open. Thus, F is continuous. Okay, so that is useful to know that no matter what topological spaces you have, if you have a function going from one topological space to possibly a different one, any constant function is continuous. And then if you have a function going from a space to itself and it's the identity function, then that is also always continuous. Okay, thank you for listening.